We have a simply supported beam with a distributed load Q. I'm going to keep the symbolic for this problem, so you could use this for any other numbers. One thing that's very important to keep in mind is if we're looking for the maximum shear and the maximum bending stress, is that if we're going to be comparing it with our moment diagram, like you have down here, moment is going to be the same place as your max shear for only prismatic beams only. What prismatic meaning that it's a constant shape throughout the whole thing. It's not tapering off, it's not getting smaller, it's not I have a big side and then a small side. It's just a straight beam. So if it is the same, then these are equal. If it's non-prismatic, then we have a little more problem. It's just we have variable I, moment of inertia, later. So let's work it out in this simple case. I have my free body diagram here already. I want to be able to find my max shear and my max moment. So let's draw the shear and moment diagrams. Okay, since this is symmetrical, if this is Q and this is L, then this side's going to be QL over 2, and this side's going to be Q times L over 2. If you could see where that comes from, the total load's Q over L, and I have 1/2 on each side. Which means that my shear diagram should look something roughly like this, where this is negative QL over 2. I go up, and this is QL over 2, and this is right at L halves. So our max shear is right here. V max, which we'll use later, is QL over 2. Our max moment is also pretty easy. It's going to look something like this. The max at L over 2, and that's going to be the area of this triangle. It's going to be the value here. So that's going to be max moment equals 1/2 base, which is L halves, times height, which is QL over 2, which will give me QL squared over 8. So I'll put that over here. And that's my M max. So let's go back. Our tau max equation, we're looking at the equation V max. We're going to have to find our Q max. I is not going to matter since it's prismatic, it's the same all the way across. And then our B is also the same, no matter what. Our bending stress is going to be M max times Y max over I, which is also constant. Okay, so let's look at the shear first. We have our V max, we need to know our Q max. Let's start with Q max. So keep in mind, I'll draw it over here. This is our cross-sectional area. For rectangles, our Q looks something like this. It makes sense that shear would be 0 at the top and the bottom because shear is an internal thing, and the most internal point happens to be right where the max Q is going to be. So this would be the values of Q, and this is going to be up and down from the neutral axis. So we have an equation given to us for the max Q in a rectangle, which is BH squared over 8. That's something that you can look up or calculate. I'd be able to do that by saying this area BH halves times my centroidal distance, which is this centroid to the neutral axis is h over 4. So the area times my y bar equals bh squared over 8. So you can derive it or just look up the formula for Q. So Q max equals bh squared over 8. V max we already had was QL over half. Let's find our I. We have a formula for I is bh cubed over 12, and b is just b. So our tau max, let's plug everything in. I got QL over 2 times our q, which is bh squared over 8. I have bh cubed over 12, and I have b. Let's simplify this a little bit. Okay, I have q l bh squared divided by 16. I have b squared h to the third divided by 12, which is going to equal, put my 12 on top, q l. I have one b that cancels on top, and I'm going to have both h's cancel on top. 16 bh, and that's going to reduce. I have a 4 in each of those, so 3/4 ql over bh. And notice that this would equal the same thing as 3v over 2a, since our v equals ql over 2 and our a equals bh. This is where this formula is derived from. So you can memorize for rectangles, my max tau, my max shear stress is going to be 3 times the max shear force divided by 2 times the area. Okay, let's look at our bending stress. Okay, max moment, we have a formula for that over here. QL squared over 8. We have our max y, which y is measured from the neutral axis, and I could go either direction. The max is just going to be h halves. And that's over our I, which we already calculated, bh cubed over 12. And let's simplify this. QLh divided by 16, bh cubed over 12 equals 12ql squared over 16bh squared. One of my h's had canceled out. And I can reduce that to 3ql squared 4bh squared. And that's it. That's actually what my answer would be. So I have, based on this general solution, I have a rectangle beam simply supported. My max shear in that situation would be this. My max bending moment would be this. And that's that problem.